Hi everybody. Today we're going to be proving the triangle similarity theorem using angle-angle. Now when we talked about similarity yesterday, to prove something similar you got to prove all the sides, you got to prove all the angles. Well, this is one of the shortcuts we have, just like we have the shortcuts for the triangle congruence. So the angle-angle similarity theorem lets us say that if we know two angles match up in two triangles, match up being congruent, then that means the two triangles are similar. And this is a great shortcut. We don't have to do any work with scale factor. This is pretty excellent. We're going to do a proof through transformations. So we're just going to talk ourselves through this one. So we have two triangles, all right, and our given is that the two triangles have two congruent angles. So angle B is congruent to angle E, and angle A is congruent to angle D. And we want to prove the triangles are similar. All right. So to get that, we need to prove that there's a sequence of transformations that map these onto each other. So the first thing we're going to do is we're going to dilate triangle ABC using a scale factor of K. And that K is going to be the ratio of the sides of DE to AB. And we're going to leave A as the center. What happens is that new triangle, A prime, B prime, C prime, is now going to be the same exact size as triangle DEF. All right? And now, once we have the right size, all that remains is for us to verify the segments are congruent. So since the dilation is a similarity transformation, and because the ratio corresponding side lengths in similar polygons equals their scale factor, for instance, A prime over AB is equal to DE over AB, then if we multiply both sides by AB, we get that AB prime is equal in length to DE. And by definition, that means that those sides are congruent. And since we know those sides are congruent, and we know that like angle A matches angle A, and angle B is congruent to angle B, if we go back and look at the picture, I've now shown, move myself out of the way, I've now shown that A and D are congruent. B is congruent to B prime, which is congruent to E prime. So with that, and using the reflexive side, I can now show that the triangles are congruent by angle side angle. So we use a composition of rigid motions to map AB prime, C prime to DEF. And since a dilation followed by a composition of rigid motions maps the triangles to each other, we can say triangle ABC is similar to triangle DEF. Let's put this into practice. We want to show the two, sorry, we want to look at this one. We want to use the angle-angle similarity theorem. So if we take a first look, it's pretty obvious that we have at least one angle is congruent. We definitely have that these right angles over here are congruent to each other. But we don't know enough to say the other angle, so we've got to do a little bit of work. We can do this any way we want. We can work with triangle CDE, we can work with triangle HGK. I'm going to do CDE. So this is 90. And that means that 26 plus angle E equals 90. 26 plus measure of angle E equals 90. And now when I subtract 26, I get the measure of angle E. Let's see, 90 minus 26 is 64. So now I've got two 90s. I've got two 64s. So I can say the triangles are similar by the angle-angle property. Our similarity statement, just like for a congruence statement, we've got to match up the sides. So we're going to say triangle CDE is similar to triangle. Now angle C is probably going to match angle K. So I'll put K first. D is a 90 and G is a 90. And angle E is 64, and angle H is 64. And there we go. Alright, so our similarity statement matches the angles. Now let's look at another example to use angle-angle. I want to show the two triangles are similar. So it's pretty obvious on this left example that we have a 52 and a 52. All right, but I need another angle. So you can do this a couple different ways. The easiest way is, the cleverest way is to use the reflexive property. Both these triangles share this angle A. So I got angle A in both triangles. I got angle ABE and angle ACD. So I can use the two triangles being similar by angle. In this situation, it's a little different. Quickest thing I see right away is this vertical angle. And now I see this marking for parallel lines. I know that's pretty important. So what I'm going to do is I'm going to extend the lines just to help me visualize a little better. So we're going to extend that line, and I'll make this my transversal. And once you do that, sometimes you do it visually, sometimes it actually helps to draw it. It's pretty obvious to see that angle R and angle T are alternate interior angles. So there's one angle, there's two angles. Triangle SVR is similar to triangle UVT by angle. If you wanted to, you could have done angle S and angle U had you chosen. Alright, so I'm going to ask you to pause your video right now and try to solve these problems. We'll be back in a moment. Alright, so for number one, it's pretty easy to show that the triangles are similar. We have so many angles to choose from. In fact, since this is an equilateral triangle, equiangular, and this is equiangular, we can actually match this up in a million different ways. Alright, there's an angle and angle. There's an angle and an angle. There's an angle and an angle. They're all the same. So these triangles, the similarity statement, you can actually write any way you want. You can write FGH is similar to RQS, FGH is similar to QRS, and so on and so forth. In this example, I find it's helpful to kind of redraw this second triangle and match it up so the pieces are kind of similar. So I kind of took DEF and kind of tilted it that way. So we have our right angle matching our right angle. All right, I have angle E is 58. And I wrote a statement for triangle CDF. These two angles have to be complementary. So 32 degrees plus the measure angle D is 90. And when I subtract 32 from both sides, I get measure angle D is 58. Therefore, 58 and 58 match up. So I can write my similarity statement. And I'm going to say that triangle CDF is similar to triangle, let's see, C is 32, and this one D must be 32. D is 58 here, E is 58 here, and both F's are 90, so I got this matched up properly. Now it asks, in this example above, if these weren't parallel lines, could the triangles be similar? So if we look above, these aren't parallel. I have no other way of obtaining any relationship between these angles and these angles. So this would actually not be possible. So the answer here would, I guess, just be no. Alright, so here's our last example. Now, we're going to use indirect measurement using similar triangles. And we talked a little bit about this in class. But here's an example. So this flagpole and this woman are both standing somewhat similar spots to each other. Alright, and we've got the sun over here shining bright, and because the sun's rays are coming from 93 million miles away, in order to reach the same spot, the rays have to be relatively parallel. In fact, pretty parallel to stay in the same spot on a 93 million mile journey. So we got these rays and they're just like beaming down, and we can essentially say that they hit the girl and the flagpole at the same angle. So essentially what we're saying is these lines are parallel. Alright. And the girl's standing straight up and the flagpole straight up, so that they make a right angle with the ground. And then if we use the ground as a transversal of these parallel lines, then this angle in here and this angle in here are congruent due to corresponding angles. So since the triangles are congruent, we can use proportions to set it up. So now we just need to work this out. Flagpole casts a shadow that's 50 feet long, and this woman who's 5'4" casts a shadow that's 40 inches long. So what we're doing is we're using a shadow to figure out how tall the flagpole is, because I don't want to climb to the top of a flagpole. Dangerous. Alright, so we got to do a couple things. I always like to have the same units here. So I think I'm going to get everything all in inches. 5 feet, 4 inches tall. 5 times 12 is 60, so this would be 64 inches. This is for that girl. Her shadow is 40 inches. And now I'll draw a similar triangle for the flagpole. Now, 50-foot shadow, 50 feet times 12 is 600 inches. Alright, so now what we want to do is we're going to set up a proportion to solve this. Alright, so I set up my proportion. I used their shadow over shadow equals actual height over actual height, all in inches. So we could cross multiply and do 64 times 600, which sounds terrible. So I'm going to simplify this. Alright, so we divide by 10, we get 4 over 60. We divide by 4, we're going to get 1 and 15. So it's going to be a little easier math. So we got to do 64 times 15, 64, 15. Let's see, 5 times 4 is 20, carry the 2. 5 times 6 is 30, plus 2 is 32. And leave this one blank. 4, 6, let's see, 0, 6. So we got 960 inches. So we get 1x equals 960 inches. But I don't think you'd ever tell someone, hey, the flagpole is 960 inches tall. So we got to divide that by 12. And when we do, we know 8 times 12 is 96. So that means 80 times 12 is going to be 960. So this flagpole is 80 feet tall. All right, hope you enjoyed the lesson. See you in class.